All right, welcome. In this video, we are going to be taking a look at acid-base reactions, these acid-base neutralization reactions, and figuring out the pH of the resulting solution. So like the products of these acid-base reactions. And so what we want to think back to these double displacement style reactions that we did in Unit 4 and writing the net ionic equations, because these acid-base reactions will kind of generally fit into this category. So as a little refresher, let's think back to these double displacement reactions, and you should be following along on your own notes here. So you should have like a blank version of this where you can kind of fill this in and complete the reactions. So in a double displacement reaction, the cations, the positive ions, switch places with each other. So in this case, the sodium is going to go with the nitrate and the lead is going to go with the chloride. And then you figure out the subscripts of these compounds by looking at the charges. So in this case, no subscripts are needed. These charges add up to 0. And over here, it looks as though lead has a +2 charge, and I can tell that because there's 2 nitrates bonded to 1 lead, and I know the nitrates are -1, so you might want to look back at your polyatomic ions from Unit 4 if you need a refresher on that. So, but I can tell here my lead must have a +2 charge. I know from my patterns on the periodic table that chloride has a -1 charge, so we need a subscript here. And then you think back to your solubility rules, and the 2 main solubility rules to know is that any compounds containing nitrates or alkali metals, those are always soluble. And then if they, lead chloride is one of the categories of things that are not soluble. Again, you can look back to Unit 4 for a refresher. So this right here would be your, what we call, well, let's balance it first. Let's put 2 right here to balance it. This is what we call our molecular equation, just as a refresher. And then we would write out the complete ionic equation by ionizing. There's 2 types of things we want to ionize. We want to ionize the aqueous ionic compounds and aqueous acids. So lead nitrate, it's ionic and it's aqueous. So I'm going to break it apart into ions. Same thing over here, my sodium chloride, that breaks apart into ions. My sodium and my nitrate also breaks apart into ions, and then I've got PbCl2. So this is what we call the complete ionic. And then for the net ionic, I would eliminate any spectators. Those are the ones that show up on both sides here. So what I would be left with is this right here. And this would be what we call my net ionic equation. And this is an example of a precipitation reaction. That is where we form a solid. So this is just some refresher from Unit 4 to give you some background going into what we're going to talk about today, which is acid-base reactions. So you might remember when we talked about double displacement reactions, we saw there were 3 types. We could form a precipitate, we could form a gas, so there's some gas forming reactions, or we could form water, and those were the acid-base neutralization reactions. So that's what we're going to go over today. So you see there's a few more examples on this slide today. You can do those on your own as a review. But let's get into these acid-base ones. Okay, so when we first did net ionic equation, you may have gotten in the habit of ionizing everything that is aqueous. So like if you look back at this example, wherever you saw an AQ, maybe you split apart into ions, and that pattern kind of worked for us back then when we were doing precipitation reactions. But we will find that in reality, really the only things we should be ionizing are aqueous strong acids and aqueous ionic compounds. Those are the only things we really should be ionizing. So what you want to keep an eye out for is other molecular substances, so not ionic, that might be aqueous but not 100% ionized. And this is something that's going to be relevant here in acids and bases, because weak acids and weak bases fall into that category. So they're aqueous, so you're going to see a little AQ label by them, but they're not ionic and they're not strong acids, so they're not going to totally ionize. So when you see substances like this, you want to keep them in their molecular form, and that's really key here. All right, so with that in mind, let's go through some, practice problems. Let's revisit these acid-base neutralization reactions here, and we'll see that there are 4 different combinations of acid-base reactions we could see. So there's strong acid, strong base. These examples we already did in Unit 4. We'll do a little quick overview of them today. But then the new ones we're going to see today are these 2. What if you have a weak acid and a strong base, or a strong acid and a weak base? You could also have a weak acid and a weak base, and we'll discuss that later on when we talk about buffers. That's another topic there. Okay, so we're going to talk about these different acid-base neutralization reactions. So let's review what these strong acid, strong base ones look like. And with these ones, again, it's kind of a double displacement pattern here. The cations switch places. And when you have a strong acid and a strong base, you'll notice your strong acid always has a hydrogen in it, and your strong base has a hydroxide. So what happens when hydrogen and hydroxide come together, they form water. So you have a hydrogen going with the hydroxide, and then the lithium goes with the bromide. Hydrogen hydroxide, we more commonly write that as just H2O, and that's a liquid. And then lithium bromide, if you look at your solubility rules, it contains an alkali metal, so it's going to be soluble. We don't need any subscripts here or coefficients to balance, so that made that part easy. So to do the net ionic equation, I'm going to ionize my ionic compounds and my strong acids. Water does not ionize because it's a liquid, and then my lithium bromide does ionize because it's an aqueous ionic compound. I'm going to eliminate my spectators, and what I'm left with is hydroxide and hydrogen form liquid water. So this is the net ionic equation when you have a strong acid with a strong base. Here's another example here. Your sodium and your hydrogen switch places. That makes water and NaNO3. Water is a liquid. When we do the net ionic equation, we will again see that the net ionic equation is hydrogen and hydroxide make water. So anytime we do a strong acid with a strong base, we should notice that these ions become spectators, like in this case, the sodium and the nitrate are spectators, lithium bromide are spectators, and the net ionic equation is just hydrogen and hydroxide makes water. Cool, so that's the strong acid, strong base. And again, we saw this initially in Unit 4. Now let's look at something new, weak acid with strong base. The key thing here is weak acids will not ionize, but the strong bases will. Okay. So now let's take a look at this one. We got a weak acid, HCN, and then with the sodium hydroxide. So your cation switch places, that makes NaCN plus H2O. This contains an alkali metal, so it's aqueous. This is water here. And then if we're going to go through and ionize things, I only ionize, I'm going to keep saying this over and over, I only ionize 2 things. Aqueous ionic compounds and aqueous strong acids. And remember, there's only 6 examples of strong acids, like HCl, HBr, HNO3. Any acid you run into that's not one of the strong 6, you're going to assume it's weak. So like HCN is not part of our list of 6 strong acids, therefore it must be a weak acid. What does that mean? That means I do not ionize it. So this stays HCN, okay? So I don't ionize that, that stays HCN. NaOH, it's a strong base. It's a soluble ionic compound, so it falls in this category. So I do break it apart into ions. NaCN, it's another aqueous ionic compound, so it does break apart into ions. And then water is not aqueous, it's a liquid, so it does not ionize. So in this example, notice I only have 1 spectator. So this makes it a little different from my strong acid, strong base. So I only have 1 spectator. So my net ionic equation is HCN plus OH minus makes CN minus plus water. Okay. And something I will point out is, if we remember back to our definition of conjugate acids and bases, HCN is an acid. CN minus is the conjugate base of that acid. So when a weak acid reacts with a strong base, one of the resulting products is going to be the conjugate base of that acid. That's something that'll be important for us to think back to later. All right, let's do one more example. Again, we're going to switch places here, the cation switch places. So you have KClO2. It contains an alkali metal, so I know it's soluble according to my solubility rules. And I'm making liquid water. And then HClO2, it's not one of my strong acids, so it's not going to ionize. But KOH is a soluble ionic compound, so it will ionize. Same thing with KClO2, it will also ionize, and then water will not. So just remember, again, these are the only two categories of things that will ionize. Aqueous ionic compounds, aqueous strong acids. All right, so when I do that, I will notice that I only have one spectator. There you go. So what's left is HClO2 plus OH minus, make ClO2 and H2O. And again, we'll see a pattern here. This right here is an acid, and the product of this reaction, one of the products along with water, is the conjugate base of that acid. All right, now let's look at strong acid, weak base. This one does not follow the classic double displacement reaction. So when you're thinking through this, what I might recommend doing is recommend ionizing things first, and then keeping in mind that the base is a hydrogen taker. If you're trying to figure out what the product of this reaction would be, let me show you what I mean. So I'm going to look down here, and remember, I'm going to ionize something if it's a strong acid. Sorry, my handwriting's getting messy there. Or if it's an aqueous ionic compound. So HCl is one of my strong acids, so I'm going to split it apart into ions. NH3 does not fall in these categories, so I'm not going to ionize it. But I know NH3 is a weak base, and I know weak bases, or any kind of base, can be thought of as a hydrogen taker. So what's going to happen here in this reaction? Well, my NH3 is going to take this hydrogen, so it's going to become NH4. And then what happens with a Cl minus? Nothing. It just doesn't really do anything. So my Cl minus is a spectator, and the reaction that happens is H plus and my weak base make NH4 plus. So notice how here, one of my reactants here is a base, right? This is a weak base. And the product of this reaction is the conjugate acid of that base. So notice here, when the weak acid is kind of neutralized, it produces the conjugate base. When the weak base reacts, it produces the conjugate acid. So that's some patterns to notice here. All right, so HNO3, it's a strong acid, so I'm going to ionize it. There you go. This right here is an aqueous ionic compound, so I'm going to ionize it as well. And let's see what might happen here. So I see that there must be a possible like weak base in here somewhere, a good like hydrogen taker. And we know that the two kind of main categories of weak bases, so examples of things that can form weak bases would be molecules containing an electronegative element, such as like nitrogen. NH3 is an example of that. Or anions. Anions could also be good weak bases because they're negatives. They tend to attract that hydrogen there. So what happens is the Cn minus is our weak base. So it's going to attract that hydrogen there. It's going to form HCN. And then the sodium and the nitrate, they kind of do nothing. They're just spectator ions. Boom, boom. So my net ionic equation is the hydrogen ion and the Cn minus ion combined to form HCN. So again, my Cn minus is the weak base, and then the product of this reaction is its conjugate acid. All right, so here's a summary of these three different reaction types here. So we've got strong acid, strong base, and what we're showing here is the net ionic equations for these. So strong acid, strong base, they always end up being H plus and OH minus makes water. Weak acid, strong base, it follows this pattern. Weak acid plus hydroxide leave behind the conjugate base and water. And then if you have a strong acid plus a weak base, that's H plus the base, and you make the conjugate acid. The general kind of pattern we talk about in these acid-base reactions is acid plus base makes salt plus water. So salt is just a generic term. It's the product of this acid-base reaction is actually the definition of a salt. But in general, it can kind of apply to any ionic compound here. So the ionic compound formed, or the ions formed in this acid-base reaction can be thought of as your salt there. And yeah, and some salts can be neutral, some salts can be acidic, some will be basic here. And notice that we notice that we say acid plus base makes salt plus water. The one example that does not actually form water is strong acid plus weak base. So this one actually doesn't end up forming water. It's just, you know, acid plus, it's just the base just takes the hydrogen and forms the conjugate acid, and that's it. So these are the good patterns to be aware of. This is kind of a key slide here summarizing those patterns. And you can kind of just look back at these examples that we saw here. So make sure you're kind of writing these down in your notes as you're going through them. And so let's think about predicting the pH of the resulting solution here. So we want to know the relationship between conjugates, acids, and bases. Okay, so we need to know a little bit about the relationship between the strength of an acid and its conjugate base. And so there's this equation on your equation sheet. It looks like this: Ka times Kb equals Kw. That means that there's an inverse relationship between the strength of an acid and its conjugate base. Oh, and I should say this equation only works for an acid and its conjugate base. Or you can think of it as a base and its conjugate acid. So if you just take any two random Ka and Kb values, they're not always going to multiply to give you Kw. But if you take like the, you know, Ka of HCN and the Kb of Cn minus, those are going to, when you multiply those, that you'll get Kw. Or if you take like the Kb of like NH3 was a weak base we just saw, and the Ka of NH4 plus, they are going to multiply to give you Kw. And right now, we're not going to use this equation right now. We're just going to talk about this relationship conceptually here. So the key thing is its inverse relationship. So and as a result, is the stronger the acid, the weaker the conjugate base. And if you have an acid that's so strong that it's one of like the strong 6, so like the conjugate of a strong acid is going to be neutral. The conjugate of a weak acid is going to be a weak base. The conjugate of a strong base is neutral, and the conjugate of a weak base is a weak acid. So this is kind of a main takeaway here. Conjugate of weak is weak, conjugate of strong is neutral. So, and you can think of it as like a, you know, a sliding scale. So the weaker the acid, the stronger the conjugate base, and vice versa. So the stronger the acid, the weaker the conjugate base. If you have a strong acid like HCl, its conjugate base is neutral. If you've got a weak acid like HF, its conjugate base, F minus, is a weak base. So weak pairs with weak, strong pairs with neutral. That's a kind of key takeaway here. And this slide is a number kind of summary of it. So when you have an anion, anions are typically the conjugate of a strong acid or a weak acid. So if you see an anion that's a conjugate of something strong, like Cl minus or NO3 minus, it's going to be neutral. If you see an anion that's a conjugate of a weak acid, then that means this anion is going to be a weak base. So some anions are neutral, but many anions are weak bases. And thinking with cations, a cation can be thought of as a cation from a strong base, like Na plus is the cation from sodium hydroxide. And so the cations from strong bases are neutral. And then if it's a cation that's a conjugate of a weak base, then it's going to be a weak acid. It's like NH4 plus, it is the conjugate of NH3. So since this NH3 is a weak base, that means that NH4 is going to be a weak acid. All right, so now let's go back to these neutralization reactions and think about what's going on there. This was a little side note. I kind of skipped past this. There's some other cations that don't fall in either category, like cations like aluminum and iron. It turns out they're actually slightly acidic. And here's, if you're wondering how that works, I've got a little summary of what's going on here. I would say don't worry about writing this equation on the AP tests or anything. I just was more of an FYI of like what's going on with some of these other cations that don't fall into one of these two categories. So, okay, let's say the ones in the green and the purple categories, the ones you should worry most about. So now let's go back to those neutralization reactions. So remember we said there's 3 different examples we went through: strong acid with the strong base, weak acid, strong base, and strong acid with a weak base. And if we look at the products of these reactions, we'll notice that when it's a strong acid with a strong base, the product is water, which is neutral. So the pH of the resulting solution will be 7. If it's a weak acid with a strong base, notice how the product here is A-, and A- is the conjugate of a weak acid. And according to what we just said there, the conjugate of a weak acid is going to be a weak base. So that means the pH of this resulting solution is going to be greater than 7. It's going to be basic. If you have a strong acid with a weak base, notice the product of this reaction is the conjugate acid of this weak base. So the product of this reaction is a weak acid. Because remember, conjugate of a weak base is a weak acid. So the resulting solution here will be less than 7. So a takeaway here is we sometimes refer to these as neutralization reactions, acid-base neutralization, but we will only actually have a neutral pH when it's a strong acid with a strong base. If you're reacting with a weak acid or a weak base, the resulting solution will not actually be neutral. And that's going to be really important as we talk later on about titrations, which is a topic we will go over soon here. All right. And so that's a summary here. And then there's some practice problems for you to try on this slide here. So try these problems and remember trying to follow, it's going to fit into one of these categories here. And as you write out this reaction, I want you to predict whether the resulting solution will be acid, base, or neutral.